Okay, let's test this out. Sound is a go. All right, cool. Okay, so we got the sound up, we got everything running how it should, and we have a exciting lecture for us today. I am not going to get all the way through this section. I've decided to neglect the piece about melon transforms and then the one involving branch cuts of the logarithm. These are good topics. You should read through it in your textbook if you want to. Don't worry, it won't be on the exam. It just it'll end up being too much of a diversion for what we do, and when we, depending on how far we get in a certain other section later on, maybe encounter something from that could mildly be related to this, it won't be in any capacity that you really need to, that won't be easy to go over again. So for the moment, let's just keep it going. So if you recall last time, what we started out with was, at a high level, we just wanted to figure out how to evaluate definite integrals, just regular old real definite integrals, right? On the real line, involving some kind of difficult functions using some of the techniques we've came up with in complex analysis. That is, instead of doing complex analysis, we are taking a small break in this section to do calculus, real analysis, using tools from complex analysis. So the first idea we explored, it's this kind of a series of random grab bag of ideas. One of them is to use rational functions of sine and cosine. So when you have a rational function involving sines and cosines, we'll say, hey, let's just suppose that we can treat these sines and cosines as, some analytic function, or function with some number of singularities that's analytic everywhere except at those places, evaluated along a contour. Then we'll use the residue theorem on that guy, and we'll, if conditions are right, be able to figure out what the value of that regular old kind of Calc 1 integral is. Okay, so we did a little bit of this, we calculated some stuff, it's just residue theorem. We got like a nice result where you could do this. This will be useful on your homework. Then we started to talk about improper integrals a little bit. We just briefly reminded ourselves about what they are. Remember that an improper integral on the whole real line is defined in terms of improper integrals on each half of the real line, and these guys are each defined in terms of limits. Okay, cool. So if those guys converge, then we're good to go. We got a few different little results that we needed for things yesterday. Then we went on to start to talk about how we could actually use these guys. So our first example, we evaluated the integral from negative infinity to infinity of x squared divided by 1 plus x to the fourth. And the way we did this is we made ourselves little half circles enclosing, going along our path. And then we did an extra one, so it enclosed our singularities for a large enough value of r, like the radius of this half circle. And then we showed that along this little chunk of the contour right there, that top arc, right, that as r went to infinity, the value of that went to 0. This just left over this piece, which we were able to calculate via the residue theorem, and we were good to go. So, kind of nice, we were able to compute the value of that guy. It turned out to be pi over the root of 2. There were a couple little pieces here, and we needed to have all these. The first thing we needed to establish was convergence of the improper integral. We needed to know it existed in the first place to use the nice symmetric form of it that we required. After that, then we needed there to be finitely many singularities in the upper or lower half plane, none on the real axis, and then we enclosed these in these half circles. Okay, finally, we wanted an estimate showing that the integral along the upper or the lower part of that half circle tended to 0 as the radius of the half circle went to infinity, and when that happened, we were able to generate some nice formulas. We got 2 pi I times the residues of f in either the upper or the lower half plane, and notice when we switched from upper to lower, we got a minus sign. The lower one, we got a minus sign. So when we're below the real axis, we get a minus sign, the negative side of it you can think of, right? And above it, you didn't get it, so bada boom, easy enough. And then, of course, we got like a nice little special case of it that is sort of convenient to use. Now what we're going to get into is another technique, and I actually won't show an example of this. I'll just tell you how to do it, because the example that we would otherwise go through, they spell it out in your textbook. It's nothing too special. It just doesn't, it's really long, and it doesn't have any insightful tricks relative to like how we're doing everything. It's just kind of computationally tedious, all things considered. It is good to know about, but the Fourier transform is a topic worth investigating in more depth than we would otherwise be able to in just an example. It won't give you that much insight, but it is good to bring up that this is a thing you can do because you might be able to use it occasionally. So, idea was we had Fourier transforms as we're defining it here. People might say it slightly differently otherwise, maybe different constants or something like that. You take a function from the real numbers in the complex plane, and the Fourier transform is a function, a complex function defined as f hat, or script f of omega, and that's 1 over the square root of 2 pi times the improper integral from negative infinity to infinity of f of x times e to the minus I omega x dx. Okay, so the key ingredients we're going to need to have to make our method for integrals of Fourier type, that is things that look like this bad boy right here, the things we'll need to have to make this work are a few things. F will have to be analytic on an open set containing the upper half plane if omega is greater than 0, that is, if there's some little constant by the ix in the integral, right? If that constant is less than 0, then f has to be analytic on an open set containing the upper half plane, right? And the lower half plane if omega is greater than 0, except for finitely many isolated singularities, none of which are on the real axis. That last piece is very important, none of which are on the real axis. This has been a condition we've had the entire time so far. Okay, so what does that mean? Well, just look at this minus sign here, the minus omega, right? So one we have is on the upper half plane if omega is less than 0. So just think about like incorporating the minus sign into omega. In that case, like if you got rid of the minus sign and just let it be part of omega, then that would be if omega is greater than 0. So above the half plane in that case, right? See what I'm saying? So it's like when minus omega is positive, then we're above the half plane, and when minus omega is negative, then we're below, right? We're in the lower half plane. Okay, so those are the two situations, and they just correspond to the sign of minus omega. All right, then the other piece we'll need is that f of z will go to 0 as z goes to 0 in that half plane. So in whichever half plane we're going to be in, we have to go to 0 as z goes to 0, in the sense that for each epsilon greater than 0, there is some function of epsilon, r epsilon, like a radius, a function of epsilon, such that f of z is less than epsilon in modulus whenever z is greater than r epsilon, and z is in that half plane. All right, cool. So let us give the statement here. Oh, wait a second. They said this is wrong right here. Sorry, I actually pulled this part right here directly from your textbook. That shouldn't be 0. That should be infinity. All right. Let me make that clear. Infinity plus or minus relative to the half plane, right? Something like that. As it flies off, as modulus c goes to infinity. We all can agree with that kind of stuff. Okay, so here's the proposition. Proposition 4.3.9. What we have is that under either the situation 1 or 2 described, or sorry, the situations 1 or 2 here, these two guys, which we'll talk about briefly. Under situations 1 or 2 described below, the improper integral from minus infinity to infinity of f of x times e to the minus I omega x dx converges to a value given by a formula down here, one of these two guys. Now, these two situations will give us, accordingly, those things. If f of x is real for real x, then we also get that the integrals of from minus infinity to infinity, the improper integral from minus infinity to infinity of f of x cosine omega x dx, and the same bounds for the improper integral of f of x sine omega x dx also converge and are equal respectively to the real and imaginary parts of this bad boy right here. That's pretty obvious if you want to think about it, because multiplying by e to the minus I omega x is just, well, what is e to the I theta or whatever, or, e to the I y, right? It's just e to the z, right? Think of that. E to the, sorry, I'm babbling right here, but it's just because you can write e in terms of sines and cosines, right? And so you could break this integral apart into two pieces, and you respectively get the real and imaginary parts of it, provided it exists, right? So that's kind of an obvious caveat. Anyway, all of that aside, let's actually state the things. So if omega is greater than 0, then if we suppose that f is analytic on an open set containing the closed upper half plane, that is the real axis and everything above it, except for finitely many isolated singularities, and here's once again a big piece, none of which are on the real axis. Okay, so we're set up, analytic upper half plane except for finitely many isolated singularities. We're going to also suppose that f of z goes to 0 as z goes to infinity in the half plane, in the sense that for every epsilon greater than 0, there's an r, a radius dependent on epsilon, such that f of z in modulus is less than epsilon whenever z in modulus is greater than that radius, and is part of the corresponding closed upper half plane. In that case, then this integral of Fourier type is given by 2 pi I times the sum of the residues of f of z e to the minus I omega z in the upper half plane. Okay, notice that is just the integrand, right? So 2 pi I, sum of the residues. Okay, it seems relatively obvious, right, when you think about it, because that's kind of exactly what you expect to get from the residue theorem, right? Cool. Basically, the entire idea is exactly the same as what we were doing when we were doing that whole half circle business, right? We'll make some kind of a curve enclosing the finitely many singularities, isolated singularities, none of which are on the real axis in the upper half plane, and then we'll show that since f of z goes to 0 as z goes to infinity, somehow the integral along like this like top part above the real axis, whether it's a square or something else, doesn't really matter, right? And so we'll be able to get away from that. So we'll do something like this. Easy enough. All right. So here, I'll erase that kind of unintuitive picture I just drew. Anyways, when you're doing the exact same thing on when the condition omega is greater than 0, if everything is exactly the same as in 1, with h replaced by the lower half plane, the closed lower half plane, then you're going to get exactly the same result, except with a minus sign, and the residues will now be in the lower half plane. Okay. Easy. So it's just like you switch the sign and then you switch from upper to lower and you add a minus because you're down low. So that's the only thing you really need to take away in terms of how to use this. There is nothing fancier than what we were doing just a little bit ago with this yesterday, where we threw a minus sign in when we went from upper to lower, right? Basically the exact same intuition can be used. It is essentially the same thing happening. Yeah, all right. Of course, we're going to get, as with the previous theorem I just showed, a little caveat. Both 1 and 2 are valid. Both these situations are valid if f is p over q, where p and q are polynomials. The degree of q is greater than that of p, and q has no zeros on the real axis. So notice this is slightly different than the previous situation, where we had p over q, p and q polynomials, where q was at least 2 degree greater than that of p, or of degree greater at least 2, or of at least 2 degrees greater than that of p, right? And q had no real zeros. In this case, q just has to have no zeros on the real axis and has to only be of greater degree than p. Okay, so a little bit less restrictive, a little tiny bit less restrictive, kind of cool. All right, this is just a good thing to look at and use. There is a worked out example that's relatively long that provides more intuition in your book, but for as much as we're going into this, it's just yet another one of these kind of tools we have. So good to mention that it does exist. It is slightly stronger than that previous one we went over, though it does have some slightly stricter conditions in certain ways. Just another tool. All right. Now on to the next kind of thing that will be more interesting. So far, notice I kind of really stressed that we always have to have our singularities not be on the real axis, because that's kind of like where we're trying to integrate across. Now, sometimes we will want to get rid of this requirement, and in this case, it warrants discussing the so-called Cauchy principal value. Ooh, I am lagging out stupidly hard. What is going on here? I didn't really do anything, so I'm not sure why I'm lagging so much. Oh boy, let's see what's going on. More technical issues? No. Okay, Cauchy principal value. Okay, so threw me off right there. All right, so far we've required that our integrands be analytic on the path of integration. This is not always the case. Sometimes we'll get singularities on the path of integration. That is a tricky business. In another case, you could also have branch cuts on your path of integration, and that might be a mess. So think about stuff with like logarithms and all that. We're going to not really talk about that one, but the case of singularities in the path is very intuitive to talk about and very nice because it gives you more of a sense of how the arguments we've done so far can be extended, and how this type of technique we've been using can be made more robust. So let's look at the value of the integral from infinity to negative infinity to infinity of x over x to the third plus 1 dx. All right. Now, this integrand x over x cubed plus 1 has simple poles at the cube roots of -1, one of which is indeed on the real axis, right? Plug in -1 and you get out, well, -1 cubed, you will get out -1. So -1 plus 1, that's 0. Ooh, not good. Okay, so we will essentially be able to use the same arguments as what we did for this guy here and for the one we talked about at the end of class yesterday and did an example with. But the paths will have to be altered a little bit. Now the singularities on the real axis will actually contribute to the value of the integral, and that will be important. However, we must take a kind of large amount of care. Namely, if f is continuous in the real line, except at, say, some point like x naught, let's call it, then the integral, improper integral from -infinity to infinity of f of x dx need not be actually defined. You could get out different things. So, for example, if we kind of start to look at how to do this, let's think about, well, if it's not defined at x naught, we could look at the improper integral, break this integral over the whole real line up into two little chunks. One of them going from negative infinity up to x naught minus some epsilon. The other one going from x naught plus some constant eta up to infinity. And both those guys, of course, are going to be greater than 0, right? So we're basically taking, instead of the, oh my God, is that going slow on me? Oh. Wow. Okay, so suppose we got some like x naught right here. Okay, basically what we're doing is we're going to go back by epsilon and forward by eta, and then we're going to integrate over this chunk, and then we're going to integrate over that chunk, and then we're going to make these guys very small, right? All right, easy enough. So the usual definition from calculus for the improper integral, both of these guys have to exist independently of each other, and they must exist as epsilon goes to 0 and eta goes to 0. That is, as I shrink these two things down and I get integral from x naught on out to infinity and integral from x naught out to infinity, right? Or, negative infinity up to x naught out to infinity, right? Each of those chunks, those guys have to exist independently of our etas and epsilons, right? They each have to exist on their own. Okay. So in those cases, it's convergent. So we do have to be careful though, because if we don't consider them on their own, we can get some kind of screwy values. So notice, if you take, say, the integral of 1 over x cubed from negative infinity up to negative epsilon, and then add it to the integral from epsilon to infinity of 1 over x cubed dx, you get Well, minus 1 over 2 epsilon squared plus 1 over 2 epsilon squared. Okay, all good. Put them together, right? You're going to get 0, yeah? Okay. So in that case, you get 0. On the other hand, if you went from minus infinity up to minus epsilon, just like before, we're going to pick up exactly that same 1 over 2 epsilon. But then if on the other side we went from 2 epsilon up to infinity and integrated, well, then I would get 1 over 2 times 2 epsilon squared, that whole quantity squared. And if you put these together, I get 3 over 8 epsilon squared. And as I take that going off towards, 0, right? As epsilon goes to 0, this will get what? Quite large, yeah? Up here we had nice cancellation, but something over something very close to 0, ooh, very big. And we have minus sign, so we go to minus infinity as epsilon goes to 0. Okay, so look, basically what we're trying to point out here is that we, in this case, our x naught, is basically 0, or is 0. But with the epsilons and the etas, we can do screwy things when we're considering them both at once, but making them be different or something, right? Like if you said eta equal to 2 epsilon, right? Then suddenly, oh man, you put them together like this, you take the limits at exactly the same time, and you're going to get out different values than if you just, took eta to be equal to 1 epsilon, right? Oh. So the value of the integral can then depend on how we let eta and epsilon approach 0. So in that case, the separate integrals, the integral from 1 to infinity of 1 over x cubed dx, and of course the opposite one from minus infinity to 0 of 1 over x cubed dx, these guys, they're not convergent. So it is useful, though, to define a principal value using a symmetric way of letting eta and epsilon approach 0. So if we take eta equal to epsilon and do the evaluation as above, then we can, it turns out, apply the residue theorem. Okay, so this is kind of like exactly like what we have here. If we set the eta and the epsilon equal, like up in this business right there, so set eta and epsilon equal, you're sitting in this situation. I made that kind of look messy, but notice you'd get out this guy. So we'll call that the Cauchy principal value. Why? Because it's like the nice symmetric way to do it, and Cauchy thought of it. All right, cool. So it's like the principal value. There's other reasons that inform the terminology usage, but that's all you have to think about. That's like a perfect way to summarize it. It's just the nicest way you could do it, right? How easily could you do both of these limits at once, even if you might separately have them not converge? If you do them together, then maybe you do, right? Maybe you get some weird cancellation just like this. Okay, so now this will let us use the residue theorem, and this is kind of exactly like what we did before, where we had to go like, hey, we need to be able to use the symmetric form of the integral, and then we can do this trick involving the residue theorem. Here we're going to do yet another symmetric form, and then we're going to say, hey, we can do this trick involving the residue theorem. So while evaluating those other chunks jointly may not have worked, we can at least say, hey, if the principal value, it's all well and good those things don't exist separately, and so it doesn't exist together. However, we can define this thing called the principal value, and that is well defined, right? And so that will be a nice little trick. So we'll allow for a finite number of discontinuities on the real axis, finite number of discontinuities in the real axis, by requiring f to be continuous on R, except for a finite number of points. We'll call them x1 up to xn. We'll put them in order like that. So we'll need these guys to converge the integral from, say, negative infinity up to x1 minus epsilon, and then the integral from xn plus epsilon up to infinity. Each of these guys will have to converge, those two, for every epsilon greater than 0, obviously, since, these two are defined in terms of limits, since they involve a minus infinity and a plus infinity. Those are improper integrals. So those guys will have to converge for every epsilon greater than 0. Then we'll do this guy, and provided it exists, we'll call this the Cauchy principal value. So what we did before was the case just with 1 point, right? That was kind of the situation we were just describing, but we're trying to say you could do it for more than that. And really all we're going to do is we're going to take the limit as epsilon goes to 0, minus infinity up to the first point of discontinuity, minus epsilon of f of x dx, and then we'll do the exact same, integrate f of x dx again from the first point of discontinuity plus epsilon up to the second point of discontinuity minus epsilon. And then from the second point of discontinuity plus epsilon up to the third point of discontinuity minus epsilon, and yada, 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 keep summing it on up to the very end of it. And notice all these other little guys, they will need to exist as a epsilon. This whole limit will need to exist, right? But these two pieces here, we have to jointly specify beforehand, right? Just like we did right up here, that they exist for this this thing here to even make sense to take a limit of. So that's a prerequisite. If those things exist, then we can form this. We could take a limit, and if that exists, then we call it the Cauchy principal value. All right, and denote it by like the PV of this, right? PV of the integral. Okay, so if you can indeed, if the nice thing about the Cauchy principal value, among other things, is that if the improper integral exists in the usual sense, right, then the Cauchy principal value is equal to it. However, it is possible to have the Cauchy principal value of an improper integral when the improper integral does not exist in the usual sense. And that is kind of what we were trying to show. It's exactly what we were trying to show with this example right up here, right? So the nice cancellation of doing it symmetrically gave us 0, while if we did it asymmetrically, either one of these chunks, we would get something weird, right? Either one of these chunks by themselves absolutely don't converge, right? And if you try to do it together asymmetrically, you can get weird stuff, right? But if you do it symmetrically, it works out all nice. Okay, cool. So that's the whole trick. All right, how will we deal with these points of discontinuity and calculate all these guys? Well, what we're going to do is we're just going to slightly modify the trick we did yesterday. So the trick we did yesterday, if you recall, basically involved us going on our little integral from minus r to r, and then we went back, made a closed path. We showed that this top part of the circle, as r went to infinity, the integral of the function along this chunk went to 0. We're going to basically do exactly the same thing, right? Except now what we're going to do is we're going to form these. Let me put a different color pen. We're going to form, so once again, from minus r to r, we're going to go right across there first, except now we're going to do these little half circles up around each one of these things, right? So here it's like we have 3. I mean, you can imagine there being more if you'd like, but we just go across here, all smooth, all nice, right? And we just do these little tiny circles, each of them of radius epsilon. So radius epsilon, right? And they're centered at those things. So it's basically exactly like what we're doing before, except we're going to do these tiny little cutouts over the places that might give us trouble. Then when we're done, we'll just, grab the final bit, do this top chunk, and we'll go all the way back. And then we'll take the limit as these epsilons go to 0, because this thing, notice, just falls right back into what we did yesterday, right? We've got basically the exact same thing, just with these little tiny bumps, but we're just exactly in a great case to use the residue theorem. I have a closed curve, finite number of singularities, something like that, right? And we're good to go. And we could do the exact same thing on the bottom, of course, in if we wanted, kind of the lower half plane, it doesn't matter. Just, whichever is more convenient to the given situation. So let's the thing we need to deal with, though, is, what have I done? Oh no. Oh boy. Okay, there we go. The thing we need to deal with is these little cutouts, though. How do I deal with the cutouts? How on earth am I going to handle these little dudes right here? what on earth am I going to do with that? So this like chunk with the cutout, I can't just reapply the trick we did yesterday to that chunk because that point is still on that dang line, right? How am I going to deal with that point being on the line? Well, it's actually a really easy little trick, and it's pretty smooth. And let me just say it, and then you're going to immediately see how it works. So lemma 4.3.10, we're going to take f to be analytic with a simple pole at z0 and gamma r to be an arc of a circle of radius r and angle alpha centered at z0. This is basically the little chunk we're going to go across, right? Circle of radius r, angle alpha. All right, easy. Then the limit as r goes to 0 of the integral of f around this contour is equal to the angle times I times the residue of f at z0. How about that? Okay, so if we have like a half circle, right? Half circle, little half circle, just going around like a little half circle. There's that singularity off there, like going up to here and then after it, right? The little chunk right here that we're going around, and maybe I'm drawing this in the wrong direction. I should probably be having us go counterclockwise, but let me actually draw that the other direction, just so it looks like this picture. So if we're going like counterclockwise, say, and there's a point right there, then what we're gonna get, obviously, is, well, what's the angle? It's pi, right? So we'll get pi I, and then the residue of f is z0. Kind of cool. Why do we get this? Why do we get this? Just think about if we went all the way around. We get like 2 pi I times the residue, right? This is exactly the original first statement of the residue theorem, the most basic form we got. Like around a circle that goes around a residue, a simple pole one time, then we had 2 pi I times the residue, right? Easy. Okay. Now, if we only go halfway, it kind of makes sense that we should just get like pi times the residue or something like that, yeah? And if we go like you know, some amount of the 2 pi, right? Like the angle, you could always sort of see that the angle was supposed to be there, right? From the 2 pi that comes up in the residue theorem, yeah? And it comes about exactly the same way. Just do direct computation and it will come up. And then the fact that as you take the limit as r goes to 0, well, it just comes from the fact that the r doesn't actually even play anything into this. It doesn't even matter, right? The residue theorem tells us that, hey, the value, it's just because the contour encloses the point. And like the deformation theorem says that if you wiggle that around without, you know, passing through that residue, it doesn't change. And so of course, as we wiggle it by varying it down in radius, it won't change at any point all the way through there. And so of course the limit will just be, well, you know, if you had the whole circle, it would just be 2 pi times the residue, right? And in this case, we're just going to get alpha, the angle that we do have, times I times the residue. Easy. Okay. And so you can imagine then that in this picture, what we should get is basically what we had from the first result, where we didn't have anything on there, except now, since what we're doing is we're going along these guys in like not the right orientation, right? We're going to the right, like along these things. They should be going the other way or something. We should maybe get some sort of a correcting factor involving these residues on the line, right? Okay, let's just push through it and do it. Okay, so let's state the result and then we can do an example of how to use it really quick. So proposition 4.3.11 will let H0 be the open half plane. So this is the half plane except for the real axis, right? It's everything above it, but not on the real axis. Okay, we'll let F be analytic on an open set containing its closure, the closed half plane. That's what we were dealing with before, right? Except for finitely many isolated singularities. Okay, fair enough. Suppose that these x1 through xn are on the real axis and are simple poles. It's kind of a specific case. So on real axis are simple poles. Then if either one of these things happens, if F satisfies the conditions of part 1 of proposition 4.3.6 except for the poles on the real axis piece, or if F is of Fourier type, right? E to the minus I omega z gz. Then the principal value of the integral exists and is given by, well, 2 pi I times the sum of the residues of f in the upper open half plane plus pi I times the residues of f along the real axis. So, okay, that's a heck of a statement, but this 1 and 2 basically is like saying, hey, you remember when we were doing all this stuff where we kept saying none of which are on the real axis, right? If all of the things held in all of these results, or if all of our assumptions in proposition 4.3.9 or the one we did at the end of the day yesterday, proposition 4.3.6, if the assumptions hold, except for the piece involving the singularities being on the real axis, right? We have that even here too, none of which are on the real axis. If we get rid of that one condition, then all we have to do to make everything work is contribute the residues on the real line. So notice the other ones get the 2 pi i's. You can think of it like this. This is the easy way to think of it. If you look at the picture, it's the easy way to remember it. All of the stuff that would be, like up here, the residues like in this chunk or above the, in the upper half plane, the open upper half plane, all of those guys, you could like put a full circle around, right? And stay inside of this thing. While all of the ones here, you can only put like a half circle around and stay in the upper half plane. So they only contribute like half as much, right? Because they're only like half in the upper half plane, right? So that's kind of the easy way to think of it, is that the ones that are fully in the open half plane give you 2 pi I and then sum up their residues, while the ones that are only halfway in the closed, or halfway, if you put a contour around it, it's only halfway in the open upper half plane, right? The only top part of it is sort of in there. Then you only get half as much contribution. All right, easy. It's kind of nice how intuitive that is, right? Like if you're looking at the upper half plane and some stuff's like on the boundary of it, then it's half of it's in there, so it only half counts. Kind of smooth. All right, now if you do the lower half plane, can you imagine what will happen? Will it be the same as before? Will we get exactly the same thing except with minus signs? Exactly, yes. So proposition 4.3.12. Exactly the same everything. I won't even just say it out loud again. Exactly the same everything, except now replace stuff with lower half plane. And everything turns out to be pretty much exactly the same, except now I've got minus 2 pi I times the sum of the residues of f in the open lower half plane, minus pi I times the sum of the residues of f on the real axis. Easy. Okay. Cool. So let's do an example. Let's check it out really quick. All right, we're gonna go back to this guy right here, the integral from minus infinity to infinity of x over x cubed plus 1 dx. Okay, so notice the integrand, let's make it a function of z real quick. F of z equals z divided by z cubed plus 1. This guy, since you've got a degree 1 over degree 3, it's like 1 over z squared, 1 over x squared for large values of x, 1 over z squared for large values of z, right? There should be no trouble with this guy for large values of x. Okay. However, though, we have some issues, namely that there are simple poles at the cube roots of minus 1, one of which is minus 1 itself, right? Oh, okay. That's on the axis. It's on the real axis. So if I'm doing this improper integral, I have to deal with that bad boy. Okay. Near that point, the function behaves like, well, what does it behave like? Minus 1 over 3 times x plus 1, right? Oh. Okay. So that's a little bit annoying to us, right? It diverges. Yeah? Does everyone see why? So just basically do the asymptotics from regular old college algebra even, and just think about what like the function x divided by x cubed plus 1 does near -1. it'll veer off, right? It'll have like a asymptote. It'll not really work that great. And so if you're trying to integrate along here, you'll end up diverging. It's exactly the kind of mess you get with the what is it? The Gabriel's horn, as they call it. What is that? Also, harmonic integrals. So it diverges. The change of sign, though, suggests cancellation. That is, here, I should just draw this picture instead of trying to say it. Basically, I'm trying to say that it goes like whoosh on one side and then whoosh on the other side. You see what I'm saying? Like this. This is a big mess. However, the fact that we have the change of sign, one part's going way up, one part's going way down, tells us that if we do this nice symmetric form of evaluation that is Cauchy's principal value, we maybe will get good cancellation. So we're going to apply these last two propositions. Okay, the poles are at z1 is -1, z2 is another one of the third roots of -1, which will be e to the pi I divided by 3, and e to the minus pi I divided by 3. These guys are just uniformly spaced about a circle, so one of them is back here, the other two are just over here, and they come in a conjugate pair. All right. They are simple poles, obviously. Residues are given by, well, we've got z over z cubed plus 1. What do? We just derive the bottom one time and plug stuff in, right? So z over 3z squared, and then plug in zk, so I get 1 over 3 times zk, right? Cancel out one of those z's with the other ones. That's the residue of f at zk. It is 1 over 3 times zk. And we have 3 different points here. Okay, so the residue of f at -1 is -1/3. Just plug in -1 for zk here. 1 over 3 times -1. Do it at e to the pi I divided by 3. Okay, this is 1/3 e to the minus pi I over 3. And then do it at minus pi I over 3, and we'll get 1/3 e to the pi I over 3. All right, kind of cool. Notice this is actually pretty neat. These guys also look like they're in conjugate pairs. It's kind of interesting, yeah? All right, so the integrand is a rational function with the degree of the denominator 2 larger than that of the numerator. So that was one of those nice conditions. We briefly mentioned that again at the start of class. That was one of those conditions from what we were doing at the end of last class, that this part 3 here that basically was a subcase of part 1 and 2. Okay, and everything is good except that we now have zeros on the real axis. So we're good. The growth condition is fine. Now we're going to use proposition 4.3.11 in the upper half plane. The principal value in this case, well, just using our formula, will be 2 pi I times the sum of the residues that are in the upper half plane. One of them will be, right? And then plus pi I times the residue that's on the real axis. Okay. 2 pi I times the one in the upper half plane, that's 1/3 e to the minus pi I over 3, minus pi I over 3, that is this pi I times the residue of f at -1, which is -1/3, right? Put them all together, I will get pi over root 3. Do a little bit of algebra in between. You guys can handle that. All right. Now, if you do it with the lower half plane, you get the same result. That's kind of cool. So in that case, you'll get minus 2 pi I residue of f at the part in the lower half plane, e to the minus pi I over 3, minus pi I times the residue of f at the part on the real line. That's -1, that residue right there. So minus 2 pi I, and then 1/3 e to the pi I over 3 plus pi I over 3. Oh, wouldn't you know it, you get out pi over root 3 yet again after a little bit of algebra. Hey, this is kind of because, look, these residues, these guys are acting pretty nice to each other, right? They are coming in conjugate pairs exactly like these two guys did. Yeah? Or at least they're flipped over. Sorry, I should say they're flipped over the axis in like a nice way, right? Okay, all good, whatever. Basically all I'm saying is that notice the situation right here, I'll write out what I'm saying, so I'm not just babbling. 2 pi I times the residue of f at, and this guy e to the pi I over 3. And then you add the residue of f at minus 1. Okay, we get out of that pi over root 3. Obviously, that's the same as on the bottom, right? So if I subtract off this one on the bottom, right? Or let's just add them together. Let's just put them together, right? And then I'll just do this one down here, minus 2 pi I res f e to the pi I over 3, or minus pi I over 3 minus, oops, it looks like a plus, minus pi I res f at minus 1. Okay, if we added these guys together, what would we get? Just think of, like, you know, just going straight down. This one minus this one. I'll just write it out. Okay, and these two cancel each other out, right? And we will get 2 pi over root 3, right? And what were the residues we had from up here? Here's what I'm trying to say. Is, so if you add them together, you get that. If you subtracted them, then you would just have these two added together instead of subtracted, and you would get double the residue right there. And you could, wait, did I make a mistake? I'm sorry, guys. I didn't have this part written down beforehand. Let me make sure I'm not. Did they mention this part in your book? They may not. I don't think they do. Oh, okay. I'm revealing my ignorance right here. Is this that essentially all I'm trying to show? I must have made a mistake in my calculation right there. Maybe I didn't. Maybe I'm just being dumb. What I'm trying to say is that the fact that these guys are nice, you know, any time where you can do it on the upper or the lower half plane, what I'm trying to highlight is that the pieces on the middle and the pieces above and below have to balance out. That is, since the pieces on the middle, the residues of those guys on the real axis, get used in both of them, it's like the pieces above and below have to be symmetric in a certain sense, right? We have to get the same thing if we go either way. And so what I'm trying to say is that you should expect to see symmetry, if not quite as nice as being exactly, you know, roots of -1. In general, you should expect symmetry. If you get something that feels very, very asymmetric and very weird, you probably made some sort of a computational mistake. Gosh, I wonder what I did wrong with that. I'm gonna have to look at that. Anyways, that is basically what we're gonna cover for this section. Like I said before, this is a pretty big diversion from what we're overall doing in complex analysis. It's just a good, it's a good thing to know that complex analysis has a lot of applications outside of the story of complex analysis. It is part of the story of many other forms of analysis. What we've done so far is an incredibly powerful tool outside of the world of the complex plane. You can use the things that we've done so far in a wide array of situations, from real analysis to functional analysis. Absolutely comes up in harmonic analysis type things all of the time. But even more surprisingly, you find stuff like this in some interesting applications of economic game theory. You find things like this come up in certainly in stuff like control theory. I mean, it's very, very, very common for people to work in the frequency domain, in engineering applications like that. And yeah, this sort of stuff, you don't be surprised if you see a weird integral and you go, I have no idea how to solve that. don't be surprised if the answer turns out to be, oh, it's just complex analysis. It's the residue theorem. And then some nice trick involving clever contours, growth conditions, and some, various shrinking, and some maybe clever defining of principal values. Or some other way to talk about the existence of something that exists, or something that doesn't classically exist, but maybe exists under nice ways of doing things. Like the principal value exists when you do these nice symmetric forms, but maybe not generally. So that's kind of the business. If you want a good reference, your textbook has somewhere in here. Here we go. Oh, there we go. Table 4.3.1, I have it up on the screen. A gigantic table describing all of the different ways that you could do these sorts of tricks. And we did a few of them here. There are ones involving melon transforms and other things that we won't do right now, or in general, but you can read about it if you want. They're just good tricks, and it's a great table to refer to if you're trying to figure out the right way to do stuff. And then after this, we will definitely, in the next section, not return, unfortunately, to the story of complex analysis quite yet. In the next section, we will continue on our weird path by talking about infinite series and partial fraction expansions. This is slightly more exciting, at least, than what we are doing in this integration case, since these are just all kind of clever art. I'm getting an ad apparently from my music. Oh, there you go. Now it's gone. But yeah, we'll get into some stuff that is still not, once again, really as much a part of the story of complex analysis, but instead is a story of the applications of complex analysis next time. I think you can do all of the problems on your homework using what we have so far. So I will probably leave them. If anyone is having any trouble with it, please let me know, and I will double check that I made them all doable given how far we got in this section. But they should be. They might. If any of them feel really tricky, let me know before you spend an unbelievable amount of time on it. Maybe I can give you a hint. Yeah, and we'll get back into it next time, and then after just a little bit more of this diversion, we will have an exam, and you will finally be able to get back to the story of complex analysis, and we will talk about conformal mappings and fractional linear transformations and a bunch of wonderful things. In particular, we'll talk about Mobius transformations, which are real cool, and it will give us a lot of physical intuition, visualize complex or analytic functions in your mind's eye quite easily. But for now, we will call it a night and have a wonderful weekend. See ya.